So, the Lincoln 205 square wave AC/DC. This thing, according to the label right here, is made in Mexico, so it is a North American product. It's supported by the Lincoln Electric Company, which is out of Cleveland, Ohio. And this thing has a shipping weight complete in this box of about 65 pounds. If I recall, and I'm going to go ahead and look this up and I'll provide links, the unit weighs under 40 pounds by itself, so it is quite portable. It's got a couple of handles on it. You can grab it, you can drag it around. It's probably how we're going to get it out of the box here. But I just wanted to go over the paperwork and see where we were at. All right, so we're going to unbox this new Square Wave 205 from Lincoln. We're going to take a look at what's in the box down here and see what we got. Owner's manual and setup material. Got a TIG torch ready to go with a flow-through DINS connector on it, or a flow-through connector. We just plug it right in. The gas flows right on out this single piece. I also like the fact that they have a cable cover over the Superflex TIG torch cable, because these things have nylon on them, and in my experience, they snag everything on the shop floor, and while they are really comfortable to use, they don't last very well. They get torn up. And once the braiding has gone off these hoses, especially on the water-cooled models, they lose all their strength. So you have to protect the braiding on the outside of these cables to make these torches last longer. And by having, although a nylon cable cover, arguably only slightly better than what we have here, it's at least going to be one layer that it has to wear through before it drags on our cable. It's a number 17 model, so it's a 3 series, uses the big consumables. And I think we've got a stubby kit we're going to try on this too. There is a consumable right there. Gas regulator. Ooh, here's our adapter cord so that we can go from 110 or 115 or 120, whatever you call it where you're at, over to 220, 230, or 240, again, depending on what you call it. Really easy to switch back and forth. You don't have to change anything in the machine. You just plug it up to power. Hey, stick electrode holder. I guess somebody's still doing that out there. I'm only joking. I do stick welding all the time. It's one of the most versatile processes and easy to do out in the field. Here we've got our work clamp. All right, so we've got a gas hose. And now the moment of truth. Let's see what this thing looks like when we pull it out of the box. Well, I'm liking it. Ooh. Sweet. Taking a look at the front panel and the setup of the machine, it looks pretty convenient. I think we can get this thing hooked up and make some welds. So we got a nice heavy duty cord with a 230 volt plug here. Should be able to get full power out of the unit. I'm also kind of curious what the maximum output's going to be on 110 on the lowest input voltage, and how much we're going to be able to get out of it, especially in AC. Because I could see this being pretty handy for doing some portable aluminum work. So you're seeing this for the first time in person, just like I am. This looks like a MIG box, right? A product that you would buy a MIG welder in, or gas metal arc welder, and it's something that I've seen a couple of different companies do, is to take that super flexible, highly tooled box, right, where we have handles and front bezels, and we've got a cool design, and go ahead and convert it from a MIG to a TIG. And then maybe even back into a multi-process unit. So as a result, we have some storage built into this machine that wouldn't normally be there. So let's take a look. Oh, hey, look at what we've got. Conveniently stored right inside this little side door, which is normally where your wire would go if you're working with a MIG machine. We have a foot pedal. So it looks like this thing's got some pretty handy storage. And if you were toting this thing around, you could maybe get everything right in that box. We'll see. We'll take it out for now. We'll take a look. I think it's the same foot pedal that Lincoln's had for years. I'm sure it's going to work just fine. And it has the optional heel rest on it, so it gives us a little bit more feel with the foot when we're using that pedal as a remote control. What do we have up here? Let's go through this setup sheet here. These are handy charts. Get you in the ballpark. Probably not going to dial everything in exact. And remember, everything is arranged with welding based on your skill and capability, based on the size of the material that you're welding, and all the other environmental conditions that go along with it. So let's take a look here. It looks like we're going from 24 gauge down around 35 amps, all the way up to 3/16, which puts us at 150 to 200 amps on DC, all the way up to 205 on AC. So we're going to have to max it out to get in that 3/16 range. And I would say that's probably pretty accurate. You might be able to do some 1/4 inch and 3/8 on this particular unit, but they're going to be small short welds and small short pieces, because that typically is going to require 250 to 280 amps in order to be able to wet out on aluminum. And might as well get this thing all set up for TIG welding. Looks like it comes with a 12.5 foot torch, which is interesting on a small AC/DC machine. Most of the time I would prefer to go with a longer 25 foot torch. Of course, here in the shop I can move around where I need to be. It's not that critical. Okay, so in most cases on an AC/DC machine, we're going to see a connection for the torch and the work, which is right up here. In this case, we've got a negative and a positive just to tell us if we're a DC where we're going to be at. So I can plug my TIG torch in to the negative down here. When we switch over to AC, the machine's going to take care of making sure that that is my electrode side, so my balance will work properly. Let's take a look at this work clamp. Your work clamp does matter. The minimum cable size makes a difference. What we want out of our work clamp is a good connection so that current flows through it. It doesn't build up heat. It doesn't take away that heat from the arc. So in this case, what we have here is what appears to be copper. Okay, so if we take a magnet right here, I don't know what you know about the properties of metals, but copper is non-magnetic, okay? So what I think we've got here is, at best, we've got a copper plating over here. I like to use brass work clamps whenever I can, especially when I'm working on critical components. These things are going to get hot. I've seen them actually, burn right in here. They've melted. They get so hot that you can't touch them. If that's happening, you have a poor work connection. Get that thing off there, get a better clamp, get a better connection. Make sure to check these so that we make sure all of our connections are tight and we don't have any issues, right? So we got a nice cover here. I like this touch because it keeps dirt and debris from getting into the Amphenol connector, especially if you're using this thing in a portable application, whether you're taking it to the racetrack, whether you're going out to the construction site, hell, maybe you're welding at deer camp. But at the end of the day, having that cap there's kind of a nice feature. All right, we'll go ahead and line up the Amphenol connector, thread this baby in. One of the things I do notice is we've got metal on metal here with these connectors, so I'm just guessing those should be nice and robust. Take the foot pedal out. That's our heel extension. I have always been a foot pedal person, right? Obviously, I learned how to weld in a shop that had benches. We did a lot of fabrication, and at first we used the foot pedal quite a bit. Once I went out and started welding in the food and beverage industry, doing mechanical contracting, that quickly changed, right? Because everything that we were doing, we were standing up, moving around, and we went to using either scratch start, lift arc, or a fingertip or a handheld remote control. We left the foot pedal on the shelf. All right, so what I'm going to do, because I like a little bit longer foot pedal. I really don't like this version because my heel will hang off the end. It's harder for me to be balanced and sensitive. You can hear in that foot pedal, there's a click before the potentiometer clicks on. So what that allows you to do is start the arc at the minimum preset on the machine, and you don't get any of that extra amperage until you press further down. So we'll see how that works. Push in our spring-loaded tabs until they pop in. And then what we've got a longer foot pedal surface, so my foot's going to fit on there more. It's going to catch on the heel rest and hopefully give me the right pivot because it allows me to balance and better control my current while I'm welding. All right, now we're going to make our shielding gas connection. I'm going to go ahead and hook up to my existing bottle, my existing regulator, and we'll just keep everything real simple for now. What these are, right, standard connection. We're going to supply it into the back of the machine where the gas valve is. This is an 11/16 wrench size. Then we're going to come over here and hook up our regulator. So when you're working with an argon bottle, this is a high pressure cylinder, and high pressure cylinders come with dual seating valves. That means when this thing is fully closed, the valve is seated at the bottom and no content should come out, right? In theory. Then we have, the same time, the dual seating valve. When this thing is open all the way, because there could be over 2,000 pounds of pressure in this bottle and putting all that pressure on that packing around the nut, we want to open it all the way, and then this thing will seat again at the top, allow gas to flow out, but it will not let the gas leak around the packing and basically bleed off into the atmosphere. So again, when you're running argon our CO2 mix. You want to run that thing fully open. All right, so we're good to go. We've got gas. I think we just need power, right? Well, I tell you what, I want to see what this thing's capable of, so we're going to go ahead and plug it into 220, and we'll look at what it can do on 110 a little later on. Okay, so I don't need a jumper cord at all. This should plug right into my existing 220 outlet. And it does. All right, now for the moment of truth. Let's power this thing up, see what it does. Okay, so if I come around to the back of the machine, power switch is right here. I flip the power switch. We'll let it come on, see what kind of weird noises it makes. Just like the fan kicking in there, right? All right, variable speed, so it slows down a little bit quieter when it's in either a cool state or in a ready state. The reason that power switches are on the back of a machine, and this is kind of interesting because it's not the most convenient place, but I'll tell you what, in a little inverter, when you run that primary power from the back of the unit where the plug comes in, all the way up to the front to that switch, and then on back down, you're taking a lot of high power voltage and current through the machine, right? And at the same time, what that can do is induce magnetic fields and noise and different things that either interfere with the inverter performance or make it fail certain tests. So by keeping the primary power isolated to the back, you tend to shield, right, the machine from the primary power and the magnetic field that it creates as it goes through the machine. All right, let's walk through the front panel. This says we're in AC TIG mode. We're set at 110 amps. I can see pulse, balance, frequency, and post flow down here, which are my most common adjustments. I have not been through this yet, so we're going to fumble around and you're going to get to work with me as I figure out this machine. Okay, so if I press this button, oh, it gives us a process selection. Pressing it again does nothing, so it looks like I can scroll using the main control knob here. So I can go over to DC, ooh, press the button in and it makes my selection. That's kind of cool, folks. This is pretty easy to work with. Let's go ahead and do that again. We'll go over to DC stick, AC stick, and back to, oh, we got to scroll back to AC TIG. Oh, I have to press the button. Now I see pulse and it says off. Balance says auto. Yeah, I don't like anything auto except post flow. So what we're going to do is, right, because this is down around 60% as the minimum electrode negative, which means 40% of the time we would be electrode positive. So you'd get about a 40% cleaning ratio, right? And the higher the electrode positive, the more cleaning we get. The lower the electrode positive, the less cleaning we get. So it's kind of a backwards control, right? We're going to turn it up to get less. So we're going to increase our balance. I'm going to start about 75. That seems to be 70 to 75 has always been my sweet spot for balance on relatively clean aluminum. Push that button again, we'll bop over to frequency. 90 hertz, all right, so that's right in the middle. I like to run butt welds and welds where we don't want to pierce through, spread that arc out a little bit, down around 60 to 80 hertz. And then if I'm doing a lap joint or a T-joint and I've got a fillet weld going on and I need to get that triangular penetration back into the root, I will crank that up to 120 to 140 hertz. Usually, like I say, 60 to 120 hertz works pretty good. All right, post flow auto. How does auto post flow work? There's 1 second of post flow for every 10 amps that you're welding at. So if I'm welding at 100 amps, I need 10 seconds of post flow. If I hit 200 amps and I end the arc immediately from 200 amps, I theoretically need 20 seconds of post flow. Why? To shield the tungsten as it cools down so it doesn't oxide, turn gray, look ugly, get contaminated. And 2, to shield the end of the weld as the weld pool cools down. So automatic post flow gives you a minimum of 5 seconds, and then for every additional 10 amps that you weld, it starts to tack on another second. So you'll have a minimum of 5, and as you get up to 100 amps, boom, it's going to automatically adjust your post flow, and it's going to give you 10 seconds, which is appropriate to protect your tungsten in the weld. At the end of the day, you can set it and forget it, put it in auto. If I go up to 200 amps, that thing's going to crank up and give me 20 seconds of post flow, theoretically in that ballpark. So that's kind of a cool thing. You can go high to low. You don't have to worry about readjusting your post flow to optimize your gas, prevent smoke in your tungsten, and yet you're not going to waste it, right? Okay, so this is interesting. We've got our TIG consumable kit here. I just happened to open it up and take a look, And one thing I like is we've adapted to a picture here instead of a drawing. So things are a little easier to see, easier to determine, right? A little bit more representative of what we're actually seeing in the box. You've got replacement part numbers here. So if you got your favorite cup or back cap and you lose it, you can go ahead and order a new one. At the same time, it looks to me like it's coming with a 2% lanthanated tungsten electrode, which are the blue banded electrodes. And I see a 1/16 and a 332. I do not see an 1/8 inch. We've got long, medium, and short back caps. It's kind of funny. This is just me. I am a long or a short back cap guy. I don't use a medium back cap, right? Medium? No. Long or short. If I need to access something, I put the small back cap on. I use a short piece of tungsten. If I'm welding out in the open air and I don't need to worry, I run a longer back cap because it fixes a whole piece of tungsten, right? Oh, I see an 040 tungsten in there too. We do have 3 pieces of tungsten. It's 040, 1/16, and 332. Arguably, when you get up to around 200 amps, welding and AC, depending on your balance, you might want an 1/8 inch tungsten just to prevent severe erosion that might occur, right? As we get up to that level, 200 to 250 amps in AC is going to start to erode a 332 electrode. The other thing that I notice is this is not a standard kit. This is a gas lens kit. So they're kind of upping what they're providing us. Now, I just want to caution you. I've never been a gas lens guy. Do they have their application? Abso-frickin-lutely, right? They can help a ton. But when I started to do machine evaluations back in the 90s, we used standard consumables for everything. We didn't use gas lenses. We didn't recommend gas lenses. The only people I saw using gas lenses were in the aerospace industry that, right, had to use stick out that was 3 times the normal recommended range to get down into a hole. Or people that were welding titanium that had to have better shielding coverage, right? So do gas lenses help? Hell yeah, they do, but they're not an essential piece of equipment. And here's another thing. I've had really bad luck using these on aluminum, and for a couple of reasons. One, I don't necessarily think we need a gas lens on aluminum. It's just my personal opinion. And two, if you get any fuzz, which often develops welding aluminum, it's going to collect on that screen. So I don't like to use gas lenses on aluminum, okay? And I have a number of experiences that back up my decision. But you do what you want to do out there. I'm going to go ahead and I'm going to use standard collets and collet bodies to do my evaluation on, and then we'll hook these up later and see how they perform. But I'm a standard collet and collet body guy. I will use clear cups when I need to, only when I need to, and I'll use gas lenses when I need to. But for me, I'm telling you, the last thing that I'm going to do, the last thing is stick my tungsten out that far unless I need to. So I want to take just a minute to talk about TIG torch parts, right? Namely the collet and collet body. I have noticed, especially as I'm doing higher amperage welding, and I think you could probably see this here, where these things start to twist and distort, right? And they don't hold on to my tungsten anymore. So I noticed when I look in the box, I got a lot of them that are a little bit distorted because I've been running them pretty high currents, right? For the torch that I use, I like a smaller torch, so I'm willing to overheat it when I need to. I've got a number 20 or the smaller collets here too, and you can see that thing twisted right up. So if this happens to you out on the job site and you don't have any extras, you could be down. So something that I have done is I have made the change to a wedge collet. And these wedge collets tend to hold a little bit differently. They don't have the slits in the end of the metal, so they tend to hold up just a little bit better, in my opinion. So that's what I've changed to. We have a number 17 Lincoln Magnum torch. Okay, there's our connection right there, power connection. I always like to check these and make sure that they are tight. If you notice any discoloration of the brass or copper in this area, it's a good indication that you've overheated the torch and your cable is probably going to fail. All right, these are insulators that go on the torch. What I do to set up a torch, right, in this case, you can see the torch should point slightly away from you when you're holding it. Don't hook it up this way, that's backwards. So what we're going to do is we're going to thread our back cap in. You want it to be threaded in. I like to go so it's still loose, but so that that O-ring is down inside the insulator. We're not going to leak gas out of there. Now, I'm going to put my wedge collet down inside the collet body just like that. We're going to thread this in, and I like to thread these in all the way. Okay, my back cap is still loose. I can go ahead now and thread on my ceramic cup. I'm using a number 8 or a 1/2 inch cup. And now I should be able to loosen this up just a little more, slide my tungsten in, tighten it back up, and it should hold the tungsten securely without using any wrenches, okay? All right, so we're gonna prep our tungsten up, sharpen it up to a point. We're gonna allow the tungsten to take its own shape while we're welding. I'm probably gonna start out in DC electrode negative just to see what this thing can do. And then we'll switch over to AC, because as we get into AC, the alternating current is gonna slightly erode the tip on our tungsten. And I like to sharpen it before I go back to DC. So while the machine comes with 2% lanthanated electrodes, which are all fine and dandy, I happen to have a box here of 332 2% seriated tungsten electrodes, and I really think there's a number of tungstens that you can use. I standardized on cerium back in the late 90s, and I really hadn't welded with anything except red or green, right? The old rule of thumb was you use green tungsten for aluminum, and you use red tungsten for everything else. What we found in the late 90s with inverter technology is red tungsten doesn't hold up very well. And green tungsten wants to form a ball no matter what, right? It's a consequence of using it. Why did we form a ball? It's a long, drawn-out discussion, but a ball will not melt and drop off. It has more surface area. So when you're welding aluminum and you're heating the tungsten, a ball provided more mass so that the tungsten wouldn't spit into the puddle. In this case, we're welding with an inverter. An inverter is going to try to keep that arc relatively sharp because we've got a higher balance setting, so we're more electrode negative, less electrode positive, which heats the tungsten. We've got a higher frequency setting, so as we're switching polarity from positive to negative, we're doing it faster. So we're not spending as much time with each half cycle in the positive cycle either, right? So that being quicker, it balls the tungsten less and allows us to use a sharp tungsten. When you use a thorium tungsten on AC, it tends to have really, really bad migration issues. Thorium does not like to ball, right? The thorium really resists it a ton, and what you'll get is instead of having a nice smooth tip with a little ball on the end, you'll have little nodules all over it that'll form, and that can cause really severe, ugly arc starts. Right in the late 90s, we started playing around with different electrodes, different settings, and I found out that cerium was outperforming thorium, you name it, right? So let's talk about the problems with thorium. It doesn't ball well. It doesn't like to work on AC. It's slightly radioactive. There's some negative things about it. So we switch over to cerium. It performs better. It holds a better point. It has better arc starts over long periods of time. And people say, well, why don't you use lanthanum? Well, at the time, 2% lanthanum wasn't available. It was relatively new. We were seeing 1.5%, and in my opinion, it just didn't perform the way that it needed to. Lo and behold, we fast forward a few years when inverters were prevalent. Tungsten manufacturers really started getting into some new formulations for the oxides that they were mixing in with the tungsten. And what they found was 2% lanthanated performed really, really well as well. Okay, so whether you use 2% lanthanated or 2% seriated, that's up to you. I tend to be a gray guy. I have used it now for pushing 30 years. And I use blue as well, right? I've got blue tungsten over in the box. At the end of the day, they both work really good. My recommendation is use lanthanated, 2% lanthanated, or 2% seriated. So we're using the blue or the gray banded tungsten, especially with an inverter power source. So now that we've got our TIG torch assembled and we have our tungsten electrode sharp, again, I'm going to make sure the back cap's relatively loose. All my other components are snugged in there. We're going to go ahead and slide in our... Might be a little bit stiff. Oh, there we got it. It's a brand new setup. So what I'm going to do is I'm going to set my tungsten right about there. Now, when I set tungsten in, I really look at a couple of things. One, the size of my cup, because in general, the tungsten electrode should never stick out more than the diameter of the cup, or you're going to lose shielding gas. That is the benefit of going to a gas lens. On the other hand, just because I can stick it out the diameter of the cup doesn't mean I want to, right? So let's think about that. When I'm welding, I like to keep my hand underneath the TIG torch like this. And if you see here, I'm at about 90 degrees to the work surface. I'm going to tip that back just a little bit, just enough so I can see it. If I'm welding on a flat surface, okay, if I stick my tungsten out and I get a little shaky, what's going to hit first? Your tungsten. You're going to bury your tungsten in the puddle, and that's frustrating. Trust me, I know. I've been a beginner before as well. So what I like to do is only stick your tungsten out as far as you need to. And then if you're welding along and you get a little shaky and you bump down, you hit the cup, not the tungsten. That's going to save you a lot of frustration. It's going to keep your arc on and keep you from having to go and sharpen your tungsten over and over and over again. So only stick the tungsten out as far as you need. Any farther than that is too much risk of contamination. Okay, so I use no wrenches on this thing, right? We did not put a wrench on it. That tungsten does not move, okay? So we're ready to weld. So your equipment manufacturer wants you to read the manual before you begin. For a couple of reasons. Namely, because if you didn't read the manual and you get hurt, it's your own fault. But I want to take a look and see what comes in the package here. There's a setup card that's going to walk us through ways to verify our connections. It tells us where the input cord is, where the gas solenoid is, the on-off. There's a circuit breaker on here, so if we overdo anything, it's going to pop the circuit breaker instead of blowing up our machine. Hey, that's a smart idea. It tells us, right, for stick, we don't need gas. For TIG, we do. It tells you to run 15 to 20 cubic feet an hour. Turn the machine on, select process, and adjust parameters. So AC TIG, DC TIG, DC stick, and AC stick. So this thing's quite capable. It's going to give us an explanation of features and benefits. Balance range. A lower balance setting results in an arc with increased cleaning action for aluminum. What I use AC balance for is to control my arc cleaning action next to the weld. So when I'm welding aluminum, if I've got dirty aluminum, I turn my balance down, it widens out the cleaning action for me. It's something I can see. Penetration, who frickin' knows, right? Till we cut that open, we don't know what our penetration looks like. Now, on the other hand, you crank that thing all the way up. On clean aluminum, you pull those cleaning lines in right tight to the bead, and you can weld diamond plate aluminum with a mirror finish without causing much surface damage right around the weld joint, because QC hates that stuff. All right, so that's my take on balance control. As we go ahead and go through here, I see post flow 1 to 25 seconds is the maximum. It says the default is auto, allows the time to be selected. It does not tell us what the range for post flow is when it's in auto mode or how it works. All right, so they also have multiple languages in here. So I'm seeing English, French, and Spanish. They come prepared. Now we've got our operator's manual, right? It's the first thing we throw away. Just kidding. Let's take a look at what's in here. Okay, we've got a warranty registration card. This is a fantastic thing. Let Lincoln know that you got the machine. And then if something pops up, they can reach out and find you, right? A lot of times that's very beneficial, especially in the case of a recall. All right, so first section of the owner's manual is all about safety. So then we go through, we got some graphical representation here. They're going to walk us through the installation. Let's see if we screwed anything up here. General description, 205 amp AC/DC inverter welding power source. It supports TIG and stick, constant current welding modes. It is thermally protected, so if we overheat this thing, it should, in theory, shut down before it blows up, right? And that's what kills a welding machine typically, is overheating in the wrong area. Welding machines in the old days were huge transformer designs because we were transforming power at 60 hertz and it generated a ton of heat as a byproduct of getting that supply voltage down to a welding voltage. And that heat over time, especially as we're welding, would build up, and that caused us to have to let the machine cool down again so that we don't melt the transformer. In the case of an inverter power source, we create our own AC inside the box. So as this thing is welding, we're no longer transforming power at 60 hertz. It's probably more like 10 to 20,000 hertz, even as high as 100,000 hertz inside the box. And as a result, the transformer only needs to be about that big because it doesn't generate as much heat. That's how inverters are smaller. We have to manufacture our own high-frequency AC so that we can transform the power and generate less heat as a byproduct. As a result, instead of a 200 amp machine weighing 250 pounds, or in the case of the last Synchrowave 250 I had, I think it weighed 390 pounds. Now we've got a machine that's in that 200 amp category, and it weighs literally less than 40 pounds that I can carry it all around. But we have to keep those internal components running at a constant temperature. That's why that fan's not shutting off. And as we start to weld, it's going to kick the fan up at a higher rate to make sure that we don't overheat the components. Let's take a look. This is 130 amp, 100% duty cycle machine in TIG. It is 205 at 25%. So that doesn't really concern me. We're up around 205 amps. We can weld for 2.5 minutes out of 10. And you'll find out that if you're a manual TIG welder, unless you're sitting in a shop and you're running production with a rotator, 20% duty cycle is about all an operator is going to give you. Because the other time they're scratching their nose, they're cleaning their helmet, they're cleaning their parts, they're sharpening their tungsten, then they come back and weld for a minute, then they got to go to the bathroom. So a manual welder is probably in that 20% category range. And if you're using this machine at home for hobbies or your passion that you're doing a fabrication project, you're probably not going to exceed the duty cycle at that current. Now, if you're doing some industrial welding, you're trying to weld 3/8 a half-inch aluminum, hey, good for you, but this is not the machine for you, right? You need to jump up on that. Okay, so as I take a look at this, I see some warning, moving parts, hot parts. I see that we've installed this thing correctly. Looks like we have, oh yeah, here's a question. It says right here in your tungsten prep, it says the tungsten should have a blunt tip. Why? The reason that we blunt the tip on the electrode is because as we knock the tip off the end of the electrode, right, we increase the surface area at the tip of the electrode so that it can weld longer and hold more heat on the tip without the point wiggling and melting off into the puddle. So it actually improves our arc stability over time. The second reason that we do that is because the arc emits electrons at 90 degrees to the grind angle, okay? So it's inverse, just like balance control. The sharper the tungsten, the wider the arc. You can look in the AWS handbook, volume number 2, welding processes in the TIG section. They actually did a test on this, and they showed that if you take a piece of tungsten and square, it produces the narrowest arc because 90 degrees is straight down to that grind angle, right? So why do we sharpen our tungsten so much then if the ideal thing is to have a blunt on the end? Well, a couple of things. The one that comes to mind the most is current density. So as we truncate that tungsten down to a point, we're achieving higher current over a smaller cross-sectional area, which gives us better current density. Gives us a more stable arc, gives us better arc starts overall. Okay, and arc starts are kind of the biggest pain in the ass with TIG welding. They always have been. So in that case, we're going to go ahead and we're going to try to taper the tungsten because it gives us better performance, but at the same time, the tip of the electrode can melt right off. So if we were to go ahead and blunt the tungsten just a little bit, it gives us more mass, and now the tip of the electrode, instead of just having that wide arc coming off that that highly sharpened electrode, we get more of the feather on the inside, that feather of the cone. The central column is the highest part of the TIG arc. When we're welding stainless, that's extremely critical, especially thin stainless, because if you spread that arc out, you're spreading that heat out over a longer area, you're going to form a puddle slower and you'll sugar the backside every single time. So a lot of this stuff is a science that goes hand in hand. And while it doesn't really matter for the average person, if you're getting into some highly technical stuff and you're a welding nerd like me, this stuff matters to you, right? And you're going to run into applications where knowing how to manipulate your machine, your consumables, and your setup could be the difference between making it or breaking it, and it's certainly going to be the difference between doing a good job and a horrible job. Do a little pre-purge, get some gas flow in there, just tap the foot pedal, hold it away from the work, make sure that we don't zap anything. Let's see how long that stays on. About 5 seconds there when I just bumped the foot pedal. So we're setting DC TIG. We're going to use high frequency start. All right. Again, I'm at 200 amps. We're going to make a puddle on here. As I am welding, you're going to find out, you're going to see that I weld on an angle towards myself. Okay. I also like to position the weld a little higher than normal because I like my TIG torch to be at about that perfect angle when I'm welding. And then my filler rod should be at a 90-degree angle to that. Okay. If I tip my TIG torch back, that's a no-no. All of a sudden now your puddle goes from being nice and round and concentric to being elliptical and elongated. you spread out the current away from the central column and you start to have a really ugly looking weld. So if you're sitting there welding thinking you're going to sit up straight like this and weld, you're gravely mistaken, right? What you have to do is you get your head off to the side, you hold that torch in the right position with your filler rod at 90 degrees, and you move your head in order to see the electrode. You do not lean the torch back. It's going to cause you issues, all right? Here, let's take a peek. All right, with one arc strike here, I got to tell you, I'm pretty impressed with how this thing welds. In DC, it is super smooth. I've got great control of the foot pedal. I love the pivot point on the foot pedal because once I found the sweet spot as far as my weld puddle diameter, I was just able to keep her going, man, and it just welded like butter. So I'm impressed with it. Let's keep running it and see what we find. Whew. I don't know what I'm cratering out to right there, but when I back down at the end of the weld and get right down to a really fine arc, it is stable. This thing is impressive. The arc start is super smooth. It's responsive as soon as I hit the foot pedal. I've got that nice arc start. You can tell that the arc start doesn't have a significant amount of amperage overshoot because it starts very, very soft. It didn't stumble once, and my shop machine is a pre-2010 Dynasty 200 that's got kind of an older arc start algorithm in it, older hardware, and I get that lightning start often. And it's really refreshing to see a machine like this come out and have a very professional arc start. That's pretty freaking cool. Okay, here's a quick slide on all of the features of the product, the specifications, dimensions, weight, the duty cycle, and then what you can expect for performance, whether you're running on 115 or 230 volt, and whether you're in TIG or stick mode. So that wraps up this video. We'll be back with segment 3 and more welding with the Square Wave 205, so stay tuned.